Swayam Prabha. Digital India. Educated India.
Welcome to the second lecture of the module Bevel Gear and Design of Bevel Gear. In the first lecture, we studied the application of bevel gear, its nomenclature, and the important nomenclatures were the pitch cone, the pitch diameter, then the pitch angle, and it was found that the bevel gears are defined from its big end. So, the pitch diameter corresponding to big end means the side from where the big size of gear tooth will look is called the pitch diameter. Similarly, we studied the different types of bevel gear based on the different values of pitch angle and different values of the shaft angle. Now, after studying the introductory part, we will study the forces which acts between a gear tooth mesh in a bevel gear, and this we will do particularly for the straight bevel gear, which are analogous to the spur gear. So, let us study the force analysis. In the force analysis, the first figure is for the spur gear and the second is the bevel gear. We just try to make a correlation between the forces which acts on a spur gear and the forces which acts on a bevel gear. In the case of spur gear, let C is the pitch point where the point of contact is, and that is given by a point C. And we have a infinitesimally small element given by A, B, C, D, E, F, and there may be a point called G also. Okay. And in the case of spur gear, the normal load Wn acts in a plane A, B, C, D. In the plane A, B, C, D, the normal load Wn along the line of action acts, and its component along the radial direction BC and tangential direction DC were determined knowing the angle ACD. ACD angle was called the pressure angle phi, and thus the component of Wn in the direction of DC or the tangential direction was Wt, and in the radial direction BC was Wr, and Wr was Wn sine of the phi and Wt was Wn cos of the phi. Now, this was the case when this top land was parallel to the axis of the shaft. Well, now if we inspect the bevel gear, then this surface, which we may say that the surface formed by joining all the top lands, that surface will be a cylindrical surface. Now when we will join the surface of all the top lands of a bevel gear, then we will have a cone, and that cone will be the face cone. This is face cone, and from the pitch lines, the cone which is formed is called the pitch cone, and the angle between angle of the axis of the shaft and the pitch cone is called the gamma. Now let us see what is the difference. This surface, the cylindrical surface, is now inclined by angle gamma in the case of bevel gear. So the plane of normal load Wn, which was acting in a plane ABCD, will now rotate by angle equal to the pitch angle gamma. So that is making angle gamma with the plane ABCD. Well, then that will be the plane along which the normal load will act in the case of bevel gear. Okay. Yeah. In the case of spur gear, the normal load is acting in the plane of ABCD, A, B, C, D, A, and along A to C. Now this plane, this top land, which is parallel to the axis, is now rotating with an angle gamma for the case of bevel gear. It means the plane of Wn for the case of bevel gear will be the plane when this ABCD will rotate by an angle gamma. So let a plane DG, this DG and this one is H, let DG, H and C, D, G, H, C, D. This is the plane which makes angle equal to this pitch angle with the plane ABCD. So this angle is gamma. So now we are taking a plane DGHCD which is making angle gamma with the plane ABCD, the plane on which the normal load for the case of spur gear was acting. So this plane will be now the plane where normal load Wn will act for the case of bevel gear. For the case of bevel gear, and that is shown in this diagram. In this diagram, this DGHGD plane is shown as A, B, C, D. So the plane on which normal load will act for the case of bevel gear is now again said as ABCD plane, but it is making angle gamma with the plane, this plane on which normal load for the case of spur gear will act. So now the angle between plane E, D, CH, and ABCD for this case is pitch angle gamma. Well, so your Wn will act along this direction from A to C. So, DC is tangent to pitch cone. So, this is the direction along which if any force is acting, then it will drive the gear, this bevel gear. Well, HC is the radial direction because it is towards the center of rotation of the bevel gear. So, this HC is the radial line or the radial direction. Well, this one, this is radial direction. This is radial, and your DC, this one, is tangential direction because it is tangent to the pitch cone. Well, from this figure it is clear that this GC is parallel to the axis of rotation of the gear, and so this GC is the radial direction, it is axial direction because it is along the axis of rotation, axial direction. Well, so normal load Wn will act from A to C. Tangential load Wt from D to C. Radial load Wr from HC, and axial load Wa GC. Well, in the case of spur gear, we have already studied that this is the direction of radial load, this is the tangential load. Now, with this, let us find the values of the transmitted load Wt, which is tangent to the pitch cone, and the radial load and the axial load. Well, so the angle ACD, angle A, C and D is the angle made by your line of action, because this is the direction along which Wn is acting. Wn, okay, Wn is from A to C, okay, Wn is from A to C. So, the angle made by the tangential direction to the pitch cones. So, in the case of spur gear, we have studied that if we have, this is the pitch circle of the pinion, this is the pitch circle of the gear, then a line tangent to these two pitch circles is the called pitch line, and the angle between line of action or the pressure line and this pitch line is called the pressure angle phi. Now, in the case of bevel gear, these pitch circles are replaced by pitch cones, okay, and if we see the big end, then there will be pitch circle corresponding to the big end for bevel for your gear and for the case of pinion. So, the analogous things are there. There in the case of bevel gear will be your pitch line and there will be pressure line, and the angle between them will be the pressure angle. So, the pressure angle is the angle between the direction in which Wn will act and the tangential direction. Tangential direction is the direction of the pitch line. This is pitch line is the tangential direction. So, this angle, that is the angle ACD, will be phi, pressure angle, and the angle ADE is the pitch angle gamma, because this is the angle between the planes on which normal load acts for the case of spur gear and the normal load will act for the case of bevel gear. Well, so tan of the phi in the triangle ACD, because in the triangle ACD the angle ACD is 90 degree. Okay. So, tan of the phi will be given by AD divided by DC. AD we say as WS, because this is the this will be the component of load which will try to separate the two loads or the two gears. Okay. So, just say that tan phi is AD divided by DC. Now, what we will do is, we will take the component of this Wn in the direction which are useful to us, that is the tangential direction or some other directions. So, in the rectangle or the area ABCD, which is shown here, ABCD, along A to C the Wn is acting and the angle ACD is phi. So, the component of this Wn along DC direction is Wn cos phi. It is Wn cos of the phi, and that is the transmitted load. And the component of Wn in the direction of BC, this is the direction of BC. BC is called Ws, and that will be Wn sine of the phi. Okay. Now, what is this Ws? Ws is the direction which will along which the if the force is acting, it will just try to separate the two gear teeth in mesh, and so it is called the separating component of Wn. So, your BC is Ws and DC is Wt. So, tan phi can be written in terms of Ws divided by Wt. Now, your BC line is perpendicular to the OC. OC is the pitch line. Okay. OC is the pitch line, and so this BC will be perpendicular to the OC, and HC, this HC will be perpendicular to OX, the axis of rotation. Okay. This angle is 90 degree. Similarly, the angle BCO, this is 90 degree. Okay. So, the force Ws is acting perpendicular to the gear tooth, and thus the reactionary force will try to separate the meshing gear. Now, we have the Ws is acting in the plane of BHCG, this plane. So, let us take this plane separately. In this plane, along BC, the Ws is acting, and if we know the angle BCG, we can find the component of Ws in the axial direction, that means GC, and component of this Ws in the direction of radial WR. So, what will be the value of this angle BCG? Let us see. The angle BCG will be the pitch angle gamma. How it will be? See, your in this triangle, this is your 90 degree. So, this angle will also be your gamma, isn't it? The angle GCO is gamma and angle BCG will equal to this 90 degree minus gamma, okay, and so you will have this we have obtained as 90 minus gamma, and so this angle is gamma. We have taken separately the area, this BHCG, in which this WS is acting, and this angle is your gamma. So, the radial component is given by WS cos of the gamma, and WS is WT tan of the phi, we have already obtained, okay. This is WT is equal to WN cos of the gamma, and so WN is equal to WT divided by cos of the gamma, and you can get this ratio as a tan phi. This WS divided by WT was tan phi, and that was used here. So, WS is the WT tan of the phi and this cos gamma, and so the radial component of the normal force Wn is WT tan phi cos of the gamma, and the axial component will be Ws sine of the gamma, and that is WT tan phi and sine gamma. The normal or the resultant force Wn is shown applied to tooth at the pitch cone surface and midway along the tooth with W. So, if you have this type of gear tooth is there and this is the width. So, this Wn was assumed to act along the tooth cone surface. This is the tooth cone surface, that means along the pitch surface, and midway along the tooth width B. This is the B. So, in the middle it was assumed to act. It is also assumed that load is uniformly distributed along the tooth width despite the fact that tooth width is larger at the big end. From these formulas we will get all the terms in terms of the transmitted load Wt, because transmitted load Wt is known to us, knowing the power which you want to transmit with the pitch diameter of the pinion and the rotation of the pinion. Knowing this, we can get the value of Wt. So, Wt is known to us, so all the forces should be obtained in terms of Wt. Okay. So, we have one of the equation, that means this Wt is equal to Wn cos of the phi. So, from this we will get Wn is equal to Wt divided by cos phi, and that is substituted, and Ws is already obtained like this. So, Wr is in terms of Wt and Wa is in terms of this. So, Wn is Wt divided by cos phi. So, that forces are shown here. Now, to determine the Wt, the main problem is which pitch diameter we have to use, whether the diameter at the big end or the diameter at the small end. But we studied just now that the normal load Wn is assumed to act midway along the tooth width B. So, the diameter should also be taken as the average diameter while determining the value of WT. So, what we are saying that if this is a pitch cone, this is the pitch cone, let's redraw it. This is the pitch cone, this is the axis of rotation, and the angle, pitch angle is gamma. Okay. So, the load is assumed to act at the mid plane. This is the your width B of a gear tooth. Let this is A point, this is your C point, this is your O point. Okay. So, capital AC is the half of the pitch diameter at the big end, and that is called the half of the pitch diameter. So, D is this, AC is D divided by 2. Now, we have to find this BC, this is the mid plane, and if a perpendicular is dropped from mid plane on the line AC, then it is intersecting at B. So, the mean radius or the average radius of this pitch cone is given by this BC. BC is the average radius, or if we see on this side also, then this BCD, B to D will be the average diameter. B to D will be the average diameter, and BC is the half of the average diameter, that is called D average divided by 2. So, D average divided by 2 is given by AC minus AB. AC is D divided by 2 and AB will be given by, AB can be obtained knowing this point, this is the midpoint M. So, the angle AMB is gamma and AM is B divided by 2. So, AB is B divided by 2 sine of the gamma. Sine of the gamma is your AB. So, D average divided by 2 is D divided by 2 minus B by 2 sine of the gamma, and so D average is pitch circle diameter of the gear, the bevel gear, minus B face width sine of the pitch angle. So, average pitch line velocity corresponding to this point M, average pitch line velocity will be given by pi d average, then revolution of this pinion, you may say NP, divided by 6000, and so WT is 1000 H, the power which you want to transmit, divided by V average. So, WT can be obtained by this way, and knowing the WT you will get the different forces which will act on the bevel gear in the axial direction, in the radial direction, and in the tangential direction, WT. The axial force on the gear will act along its axis of rotation. This is the axis of rotation, and so the axial force will act along this. This is the direction of WAG, and its arrow will be decided by the direction of radial load on the pinion. The direction on the radial load on the pinion will be towards its axis of rotation. So, W radial on the pinion will be along the direction of Y. So, just opposite to that will be a force which will act on the gear, and that force will be the axial force. So, WAG, that means axial force on the gear, will be just opposite direction to the radial force on the pinion. Similarly, the axial force on the pinion will be along the direction of rotation of the pinion, and the direction of rotation of the pinion is this one, x-axis. So, at the point of contact, the axial force on the pinion will act in this way, and its arrow will be decided by the radial force which will act on the gear. The radial force which is acting on the gear is in this way along its axis of rotation, that will be W R on the gear, and just opposite to that a force will act on the pinion, and that force is in the direction of the axis of the pinion, and so it will be the axial force on the pinion, and that is given here. That means the tangential force on the gear will equal to minus of the tangential force on the pinion. That means tangential force on the pinion and gear will be same, but their direction will be opposite to each other. Now, the axial force on the gear, will be minus of the radial force on the pinion. It is clear here. Both are in magnitude same, but the direction will be opposite. Similarly, the radial force on the gear is acting in the opposite direction of the axial force on the pinion. So, WRG will be minus of the WAP. That means radial force on the gear and the axial force on the pinion will be same in magnitude, but their direction will be opposite, and so WRG is equal to minus of the WAP. This is a typical problem of determination of forces on the bearing and determination of forces at the pitch point for the case of bevel gear, and this problem says that the dimensions of a pair of bevel gears are shown in this figure. The gear shaft G delivers 5 kilowatt of power, and so H is 5 kilowatt, and RPM of the pinion is your N of the pinion is 500 RPM. Okay, of the pinion shaft. Consider a pressure angle of 20 degree, phi is given as 20 degree. Calculate the tooth force components for the pinion and gear. So, knowing this, what we will do is, first of all, you have pitch circle diameters from this figure. This is 100 and this one is 200. 200 is the your D of the gear, and D of the pinion is 100. So, knowing D of the pinion and knowing the pitch angle, you can find the pitch angle will be this one for the case of gamma pinion, and pitch angle for the case of gear will be this one, gamma G. Now, we have a relationship for this gamma P and gamma G in terms of pitch circle diameter of the pinion and gear, and that you can easily see from this triangle to determine the gamma p. Okay. In this triangle, this length is dp divided by 2 and this length is dg divided by 2. So, tan of the gamma p, because the shaft angle is 90 degree. Shaft angle is 90 degrees. So, we can apply this relationship. Tan gamma p is equal to dp divided by 2. So, let us only write dp, because on the denominator we will get the dg divided by 2. So, dg. So, from here you may get the gamma p. Similarly, you can get the gamma g. So, knowing gamma p, knowing np, you can find the average diameter d average. Knowing d average, you will get the Wt with the knowledge of h. So, Wt is known to us. We have phi, we have your pitch angle gamma p and gamma g. So, you can find the forces Wa, Wt and Wr on the gear and pinion. Thereafter, you can also get the bearing reaction. So, with the similar analysis which we did for the case of helical gear, you can draw the free body diagram with reactions at the bearings and the gear forces acting at this mid of the face. You can find the reactions. So, this is the way the force analysis is done. Now, next thing after getting the force analysis is the stresses in the bevel gear and the strength of the material. Now, stresses on the bevel gear are they act in a similar way as we studied for the case of spur gear and the helical gear. That means the mode of failure will be bending fatigue and the surface fatigue due to contact stresses. So, two types of stresses will be there, bending fatigue and the contact fatigue stresses. So, next our aim will be determination of these two stresses, and thereafter we will find the strength of the material of the bevel gear, knowing the actual condition, because the strength data we will get from the literature, and in the literature the strength data are for particular set of condition, and for our case the condition may be different. So, there are two modes of failure in the case of bevel gear also: fatigue fracture due to fluctuating bending stresses at the root of the tooth, and surface fatigue pitting of the tooth surface. So, bending fatigue stress we have to determine, the surface fatigue stresses we have to determine, thereafter bending fatigue strength and contact fatigue strength. Now, in the case of bevel gear, the mounting may be of different type. That is, in a typical bevel gear mounting as shown below, for example, one of the gears is often mounted outboard of the bearing. That means, in this case you see the shaft of the gear has simply supported type of arrangement. You may say this will be like this. Here is the support, and in the mid the bevel gear is mounted. The bevel gear is mounted in the middle. So, it is a simply supported beam with a radial load or the axial load acting at the midpoint. And for the case of pinion also, the same type of simply supported arrangement is there. This is called the both gears straddle mounted. But in some of the cases, the shaft may be supported like a cantilever beam. So, here we have a shaft and it is supported at this point and this point, and the gear is mounted here. So, the forces will act at this point due to transmission of load, and the radial force will act just like a cantilever beam type of arrangement. This may be said as a fixed point, and this is the beam where a bending moment is applied or the load is applied. So, both gears overhung. In this case, One is overhung, another is straddle mounted, simply supported and cantilever. Here both are cantilever type. So the difficulty with this is when we have both the gears in a cantilever beam type of thing, then there will be more deflection and there may not be uniform force transmission all along the width. So force may not distribute equally along the width of the gear, and here this will be the case where the force will be uniform throughout its width if other condition like means the surface finish and others are good. Another difficulty that occurs in predicting the stress in bevel gear teeth in contrast to the spur and helical gear is the fact that the teeth are tapered. You see, this dashed line is showing the teeth for the case of spur gear or the helical gear, and this bold line is showing the top length for the case of bevel gear. So the teeth are tapered. Here at the small end the thickness will be T dash and at the big end the thickness is T. Thus to achieve perfect line contact passing through the cone center, the teeth are to bend more at the large end than at the small end. To obtain this condition requires that the load be proportionately greater at the large end, because at the large end you want more deflection. Because of this varying load across the face of the tooth, it is desirable to have a fairly short face width. So if face width is short, then will be a better condition. Now let us study the bending stress and strength. The equation is very much similar to the spur gear because this straight bevel gear is analogous to the spur gear. So the equation is same as we derived for the case of spur gear. It is equal to the transmitted load Wt divided by face width. For the case of spur gear, the face width was taken as F. For the case of bevel gear, it is B. Well, because in the case of spur gear, the addendum was taken as A and the dedendum was taken as B, but in the case of bevel gear, we have taken HA and HF, and so B is taken as the face width. So in place of F, you can write B for the case of bevel gear. J is the geometry factor, then velocity factor, overload factor, the mounting factor or the load distribution factor and the size factor divided by another factor Kx. And the strength equation SFB is the fully corrected strength, fatigue strength, and this is the strength obtained from the literature. The strength obtained from the literature is corrected by factor, the life factor, temperature factor and the reliability factor. And similar to the spur gear, we will determine the overload from this table, knowing the character of the prime mover and the character of load on the driven machine. Note that this table is for speed decreasing devices, where the bevel gear mesh is used for reduction of the speed. For speed increasing drives, add 0.01 capital N divided by small n. Capital N is the RPM of the gear and small n is the RPM of the pinion square, or 0.01 ZG divided by ZP, number of teeth on the gear divided by number of teeth on the pinion square, to the above factors. Then velocity factor or the dynamic factor Kv dash for the case of bending, and the same is for the surface fatigue Cv. Okay. Similar to the previous analysis, we will determine the value of Kv either using the quality factor and the equations. This equation Kv dash is A divided by this one, A is given by this, B is given by this. B is in terms of quality value, and the quality value, if it is given, then directly you can get the value of Kb knowing the pitch line velocity. Okay. So, the maximum recommended pitch line velocity is associated with abscissa of the terminal points of the curve in figure, and that the maximum value of pitch line velocity will be obtained for a particular quality value with the help of this formula. The size factor for bending is given from this equation, knowing the module at the big end, and the Ks is 0.5 for the module less than 1.5 mm, and it is given by this formula if it is in between 1.6 mm to 50 mm. MET is the module based on the big end. Now, mounting or load distribution factor Km or Kh is determined from this formula, and Kmb in this depends on what type of mounting is there. If both member are straddle mounted, it means both the gears are mounted like a simply supported beam, then 1. If one member is simply supported, other is like a cantilever, then it is 1.1. If both are like a cantilever, then 1.25. Or you can use figure 2.2 on our slide. Now, lengthwise curvature factor for bending strength, K factor, that means along the length the teeth are tapered, and so that effect is taken with the help of this Kx. Now, Kx is taken as 1 for the straight bevel gear. Now, the mounting factor Km can also be determined from this table. Both gears straddle mounted, then 1 to 1.25. If this is, then this one. If both are like a overhung or cantilever beam type of arrangement, then 1.25 to 1.5. Then the geometry factor J, which is used in the bending stress equation, can be determined from this figure, where on the y-axis is the number of teeth on gear for which geometry factor is desired. So, if you want to determine geometry factor for the case of pinion, then you will select the value of Z pinion on this axis, okay, and along the x-axis here the number of teeth in mating gear is given. So, you will select a curve corresponding to the number of teeth on the mating gear. So, in the gear, let the number of teeth are 100, then you will select this figure. If number of teeth on the gear is 80, then you will select this one, and the intersection will give you the value of geometry factor that can be used. Now, this is for the straight bevel gear with 20-degree pressure angle and 90-degree shaft angle that should be taken into account. Then permissible bending strength equation is given by this one, and the factor, life factor, is determined from this or a figure number 3.4, which is given in the coming slide. And the temperature factor Kt is given from this formula, and the life factor can be determined from this figure. So, accordingly the reliability factor can be determined. Knowing the reliability for which you want to design your gear, you will use a particular formula to get the value of Kr, or you can use this table also, and in this table one should be careful, because here the Kr, the reliability factor for bending, and this is the Cr reliability factor for the surface fatigue. For the case of Kr applicable for bending, the tooth breakage is sometimes considered a greater hazard than pitting. In such cases, a greater value of Kr reliability factor for bending is selected for bending. Okay. Now, at this value, plastic flow might occur rather than pitting. Well, for this particular case, this is given here, and for this particular case from the test data extrapolation. Now, the strength, fatigue bending strength from the literature is obtained, and in the literature different curves and graphs are given, okay, and tables are given. So, this is particularly for giving you the allowable bending strength for through hardened steel gear, reliability 99%, temperature this one, and life equal to 1 to 10 to the power 7 cycles. So, knowing the grade of the steel, you can use these formulas also to determine the value of SFB dash, these formulas. Or you can use this table, and depending on the material of the gear, heat treatment and the minimum surface hardness, you can get the bending fatigue strength SFB dash in megapascal. This is for the iron gear. This data provides you the bending strength SFB dash within the bracket terms are in megapascal. The contact stress and strength. We know that in the case of gears, at the point of contact, complex contact stresses occurs, and using the Hertzian contact stresses, we have obtained sigma h, and these are the different factors which are used to modify considering different operating conditions. And this is the equation of the strength, and this is the strength which is obtained from the literature, and the value of strength obtained from the literature is multiplied by different factors if the condition is different than the condition for which this SFC dash was determined, because this is for life 1 into 10 to the power 7 temperature, room temperature, or up to 120 degrees centigrade, and reliability equal to 99. Okay. So, in the surface fatigue equation or the Hertzian stress equation, the value of velocity factor, overload factor, mounting factor, and they are determined from the bending fatigue analysis. The size factor Cs is different, and it is given from this formula, knowing the face width. Okay. Then Csx is called the crowning factor for pitting resistance. The teeth of most bevel gears are crowned in the lengthwise direction. That means the top length will not be straight, but it will be curved. Okay. This will be the gear in the lengthwise direction during manufacture to accommodate to the deflection of the mountings. So, this crowning factor for pitting resistance is 1.5 for properly crowned teeth and 2 or larger for uncrowned teeth. The elastic coefficient I, which is used in this surface stress equation, is obtained from this curve, knowing the number of pinion teeth and number of gear teeth. You will select this one and you will get the geometry factor I. The stress cycle factor for pitting resistance CL is obtained from this equation, or you may use this curve. The hardness ratio factor to accommodate the different hardness and to accommodate the RPM, different RPM of the gear and the pinion, the hardness correction factor is used, and that is obtained from this figure. This is in terms of surface roughness. Knowing the surface roughness, you can use this to determine the hardness ratio factor. Hardness ratio factor for pitting resistance can also be determined from this equation. In the preceding equation are valid when Brinell hardness of the pinion divided by Brinell hardness of the gear is greater than or equal to 1.2 but less than or equal to 1.7. Okay. And knowing the surface finish, you can use this formula also in place of the figure shown in the previous slide. The reliability factor and is determined similar to that, but the reliability factor for the pitting resistance will be under root of the K. Fatigue pitting strength, this is the strength obtained from the literature, and these are the correction factor, and this is the fully corrected pitting fatigue strength. These are the tables. Okay. Then the summary. In the straight bevel gear, the geometry is determined from this one. From the force analysis, we determined the value of Wn, Wr and Wa, and from the strength analysis we get all these. Then this equation was obtained, and different equations and figures are given to determine the value of velocity factor, overload factor, mounting factor and the size factor and the mounting factor. So, crowning factor Kx. For the case of fatigue bending strength. This is the equation, and different equations and tables and figures are given from where you can determine these values. This is the summary for the pitting resistance, and this is the equation for pitting stress, and the different tables and formulas are given to determine the correction factors. Thereafter, the factor of safety guarding against the bending fatigue will be a fully corrected bending fatigue strength divided by bending stress. And for the case of pitting resistance, the factor of safety will be fully corrected surface fatigue strength divided by Hertzian stress or the contact stress which is acting to the whole square, and this whole square is done to make the linear relationship between the transmitted load and this one. Now, design of a straight bevel gear mesh. Useful decision set for straight bevel gear design is, we have a priori decision like what function we want to do. The design factor means the factor of safety we want to make, the tooth system, tooth count, and the design variables are the pitch and the face width, quality number, gear material, core and case hardness, pinion material, core and case hardness, and accordingly we will check whether the factor of safety which we want to achieve is achieved or not. Then the face width will be within this range, that means minimum of the cone length divided by 3 and 10 times the module. Okay. In bevel gears, the quality number is linked to the wear strength. The geometry factor J for the gear can be smaller than for the pinion. Bending strength is not linear with the face width because added material is placed at the small end of the teeth. Consequently, face width is roughly prescribed as either this formula or this one. So, in this module, we studied about the bevel gear, its shape which is other than the spur gear, and the helical gear analogous to the spiral bevel gear. And thereafter we studied the nomenclature. We found the force analysis, the forces which act on the bevel gear in mesh, the axial force, the radial force, and the transmitted force. And thereafter we found the stresses which acts on the bevel gear due to transmission of power from one shaft to another shaft, and we determined the factor of safety. So, the factor of safety will be determined separately for the pinion and gear considering bending fatigue and the pitting resistance or the surface fatigue, and the smallest factor of safety will give the area on which we have to give more attention. Thank you.